So in the previous video, I discussed the biharmonic function in a detailed manner. Let me just go back to the Notion where the lectures are. So, and here is ABAQUS file. Before going further in this lecture, let me show you an interesting code which I have developed, and let me see if I can find this code here. Yeah, here it is. Let me try. This code visualize the LET concept, and the architecture of the code is somewhat like this. First it need the libraries that you need to install for it. Then we have a maximum radius for the code, and then we assign layer thickness here, and then we define a specific location for the wheel and the radius of the wheel, and further we apply on that radius pressure, right? And after that it create a loop here, and for all loops when first it's complete here, it check the depth of the layer for the position of the tire here. Then it go back here, and if it does not satisfy the equation, the condition here, it just gives us the initial pressure for the wheel that we are calculating. And then after that it updates the frames for each of the load that we are assigning to it, to give us an overview of the load and the moment here. So let me try. Let me open this here. It will take some time because I launched the laptop right now, and I need to show you this interesting code. If I haven't changed this code, I don't know. I don't remember exactly, but let me show you. If you want to copy this code, I will show you the load number, sorry, the line number, so you can pause the video and you can see how does this code look like, right? So this is for an animation video, just for the ABAQUS profile, to show you. It's not something what we are looking for, but it's just a concept here. And I think this is module 5 in this course, so I will go to the modules later. So let's just run this module and see what's going on here. So it will, so far I remember, it will give me an animation for the visualization of the a crude form of LET theory. It's not something which is refined. So anyways, let's go to the lectures here. We were in module 5. Yeah, here. Yes. So we were here, and this is the animation that I generated with the Python code, and the syntax and architecture of the code is visible here. It's not something in the form of a standard format. It's actually a visualization that if you are studying LET theory, the stress distribution that we are seeing here, the vertical stresses should be in this format, while the horizontal stresses are the deformations that we are studying right now here will be in this format. So let's go to if you are at this course and you have purchased this course, you will find out this article here as well. This code is for biharmonic function, and in the previous two videos I discussed this code in very detailed manner. So just in case if I want to include comments on it, I can edit this file here, but I don't want to edit this file here right now. These are the integration schemes that are applied on this biharmonic function, and we got the visualization there. Then we have this radial displacement function, and this radial displacement function in biharmonic equation format, it is derived from biharmonic equation, and it's actually create for us the radial displacement visualization. So in this format it will give us the results. It's not something we are looking for. It is just an animation that I'm trying to show you. So I will close this, and I will go back to the paper. Now in this paper, this function which I discussed in detail, actually this function that I discussed here is the standard format of biharmonic function, and here these are the derived equation from it. So this equation 2 which you are seeing right now here, it is the derived equation from biharmonic function, and it's actually dependent on integration scheme of biharmonic function which is given here. So the biharmonic function is dependent on two parameters, which is R, which I discussed in detail, and Z, which I also discussed in detail. So if you are studying this LET model, right, so you should be familiarized with this equation, and this is the base for the differentiation and adding a more in-depth concept to your finite element analysis if you understand this theory here. So I also discussed these integration parameter A, B, C, D with subscripts I in term of M, and then this radial displacement. This radial displacement is actually derived from the biharmonic function, right? So it is the function of biharmonic main function. It's dependent on biharmonic function, and it's also dependent on the UI, right, which is the Poisson ratio of the layer, and EI, which is actually the modulus of elasticity, right? So I'm not going into the detail of derivation of this function because I don't have any touchpad right now or notepad which I derive this. So I will skip the derivation, but I will discuss the code here. The code, if you are watching this video series and you have the course contents and this detailed lecture, you will find out that this radial displacement code is actually the code that right now I am compiling here. So the architecture of the code is very simple. The libraries are important, then these integration constants are defined here, but here we need modulus of elasticity and Poisson ratio to define for the layer, and since in ABAQUS we are defining only single property here, you can see here these are the assumed material that I discussed in the previous lecture, and we only have modulus of elasticity and Poisson ratio. So I will assume this is a 0.5 distance and this is a 1 distance here, right? So let me just close this, as well as I don't need this code anymore, so I will close it. This was for the animation that I discussed the previous in the previous uh, compilation of the code. So let's just go to this code right now, which represent equation 2. If you remember, I discussed this syntax format here, and the syntax format actually represent this nomenclature. That, for example, if I am writing here combined with equation 1, it means that it's totally dependent on this biharmonic function. And this biharmonic function is present here in this article, which I mentioned, that it's dependent on this biharmonic function. It's dependent on modulus of elasticity and Poisson ratio. So these are the input parameters, Z, R, and thickness H, right? So thickness is HI, and if we are talking about the vertical displacement, then we need to do derivation and integration as double derivative with respect to Z to get the vertical displacement, right? And if we are doing partial derivative, we will get the radial displacement here, right? So this term is constant, and this term is given over here, and this flow here. Now it's in a more detailed way. So look at here, we are computing the second derivative with respect to R, and this is actually the equation. This is the second derivative here, right? And other than that, if I see further here 1 plus nu I over ei, this I can visualize over here. But before that, let me try with this one. The reason is some of the code lines are not visible here, I think so. So if I switch on debugging, I will see the full code here. So then I can discuss in the end of this code that we have this full derivation over here. So we have the second derivative here, right? Then we have the mixed second derivative with respect to Z and R. So these are the parameters. Then further we discussed this 1 plus mu divided by E. So this is the radial displacement that this code is calculating here, and then it is plotting for us the radial displacement right now. So then we got these constants, etc. So this debugging, I'm not going to let this debugging mode switched on. It's very difficult to explain the code here, but we got what we were looking for. This is the main equation that we are right now discussing, and this is actually equation 2, which is given here in this lecture. If you have the lecture notes, you will understand that these are the parameters which we are studying right now. So here we are expecting this radial displacement to be in consistent direction with respect to these notations here. And if I go to load the lecture here, and so let me go to open the ODB, and this is the CAE file. But I don't need CAE file, I need ODB file here, which I simulated last time, and it is actually right here. So if I click on OK, I will see the simulated file that we discussed last time, and the mesh is very rough here, you can see, but still I tried my best to make it a smoother mesh. And if we look at the displacement, So right now you need to be very careful about the notation according to the LET theory that you are studying right now. The radial displacement, the coordinates that we are expecting here, the radial displacement should be in this direction, right? So since it is a symmetrical model, and if I look at here at this axis, a global coordinate system, the x-axis is actually from the axis of symmetry toward the width of the road, and this is the axis of symmetry that we discussed, right? So what I'm expecting here is this this ui, the radial displacement, is actually from the center line or axis of symmetry, and the axis of symmetry is I think it's given here. This is the axis of symmetry that we considered, and this axis of rotational symmetry. So this axis of rotational symmetry that we are seeing right now, as in if I go to the load module, actually this is the rotational symmetry here. So move to left, move to left, axis of symmetry. This is actually what you can see here. So with respect to this axis of symmetry, if you are simulating your file, you actually need to make sure that if you are studying this, you first need to understand the nature of the radial displacement. So let me visualize the radial displacement for that, and let's just open the radial displacement here. So let's keep it 0.5 meter, right? And let's keep it 1, the depth is 1 here, and we have assumed 3500, whatever unit it is, and 0.35 with respect to this. So then I am going to actually run this simulation, right? So I am expecting that the radial displacement should be 0 at the axis of symmetry location, or the starting point of the graph, and then it will increase and then decrease. So that's what we are trying to visualize here. And yes, here we go. This is approximately 0. And then this radial displacement is increasing, and then it is again decreasing here. So what is actually means here, if we consider the radial displacement, we have two magnitudes, one in y direction, right, here, and another in this is in x direction, and this is in y direction. So in y direction, if we are representing in vertical position, this radial displacement that we are seeing here, it should be something like this, right? And if we talk about the magnitude, this is where it should be 0, and it should increase something like this. So at this point, this is the magnitude, and if we discuss u1, so we are expecting here that this u1 at this direction, we have a distance r here, so it should be a very smaller value at these regions, and then it will increase here. So let's go to the path here, go to continue, and look back at the graph here as well. This pattern is very important here, right? So if we are considering this radial displacement, we should consider this pattern. So let's before that, let's go to create a path in your ABAQUS file, and then add before we need this, we need to have this pattern here. So I will create a path on the top surface of this 2D profile, and I am going toward the radius direction. So I will show you what does it mean. I can also visualize this with respect to you know, the vectors notations, but let's do it in this way. Let's go to ODB path and plot it here. Look at here, it is approximately 0. Then you can see this is increasing, and this is decreasing and then increasing in this pattern, while the sign negative show this, that this is increasing and then decreasing. So if we change the sign, it will decrease and this will increase in this manner. But since it is a very crude pattern here, right, so that's why I demonstrated it in this manner. If you make it a smoother mesh, a very smoother mesh, you will notice that this radial displacement will show you this behavior. So what we have here, we have a value of z. This is radial displacement, right? So it is approximately, if you look at here, 0.007, something like this, and this is approximately 800, right? And here we have this value here. So if we convert it, we can see that the unit consistent units, we can get with the consistent units the correct estimation from the results that we are using here. So now let me show you this using the graphical vector representation. If you are using the magnitude here, this is actually a scalar representation, but if you are using U1 in U components, these should be vector representations. So let me just try to isolate the elements, and I think the easiest way to do is to do it on non-deformed contour shape here. So click on done, and then let's switch back to the same pattern. Let me switch on here the results for, I think here is the fiber orientation, this is the symbols. So look at here, actually if you notice what I was trying to discuss here, that this radial displacement should be 0 right exactly at the top of the center line, and a symmetrical line, and the symmetrical line is this one, right? And I defined this portion as an A portion here. So I was expecting this radial displacement at this line should be 0, which from LET I am getting right now here. And if I look at the ABAQUS graph here, so what it is showing me, the radial displacement is showing me here as 0, and that vector which I am seeing here, that 0 vector is visible here. So that's what I was trying to convey, right? That if you are using this equation from LET theory, and you are using this in ABAQUS, you are getting the same results, and the radial displacement should increase at this portion and then decrease in this portion. But since the signs are positive here, so that's why we are seeing here. If we try to change the sign, we will get what we are looking for here. So let's see, let's put a negative sign here, and let's just run this simulation. So that's what we will get. Not simulation, sorry, I'm talking about the results here. So look at here. Now let me show you this right now. At this pattern, there is a little difference at the data. at these points, but if you change these integration points in all these steps, you will observe here similar phenomena. So I'm not going in detail to these discussion. If you have the code, you can change these parameters by yourself, because it takes a lot of time to get the right parameters. But my struggle was to show you that if you are using the radial displacement, it should be minimum at the face of the central line, then they should in term of sign decrease here and then increase here, which I showed here as well, right? Look at here, this is the maximum contour. In term of sign, it is minimum, so it should be 0 here, then it should be minimum, then it is reversing a direction here, right? So that's what I'm trying to show you. And even if I go to the annotations, let me try the legends, and instead of scientific format, if I apply a fixed format here and apply this here, click on OK. So now look at the contours here, look at the contours here, and look at the contours here. So you can see the red one is showing it's 0, then it is decreasing at this portion, and then again it is increasing, which is what we are observing here. It is 0, it is decreasing, and then it's again going back to its position, and the limits are almost same except the units. So I'm not aware of the units right now because I'm using a crude data, but the pattern and the nature of the data which we are getting with this Python code is same for this multi-layer system that we are right now studying. So this is the concept of the radial displacement. I have no other way to discuss the nature of this data, but anyhow, I think it should be clear right now. So this is for the rigid pavement, which I did not consider in this model. Anyways, if you are studying the radial displacement pattern, you should find out this nature in your data. And if you are studying the vertical displacement, so for vertical displacement, I think I should discuss the other details. This should be for equation 2. So for equation 2, look at here, we have a U radial displacement. Sorry, I think not, this is for radial. I'm talking about the vertical displacement. So this is for equation 3. And for equation 3, let me show you, we should have that equation here, which is W. Again, we need the radial displacement because this equation is dependent on equation 1 and equation 2. Equation 1 is for biharmonic function. Equation 2 is for radial displacement. So let me show you that in that research article here. You can see here, this is for biharmonic function. This also involves this, the double derivative also involves the biharmonic function. Then we have UI and E, right? And we also need this biharmonic function is only the single function in which it is dependent on. So if you are studying this, let me properly check this code again. Yeah, I'm sorry. This is dependent on equation 2 as well, the radial displacement as well, which is obvious here. But there is one confusing pattern here. If you look at here, the sign of this for Poisson ratio, it is different, while for radial displacement it is different. So you should not confuse yourself in it. And if you look at the vertical displacement, so for vertical displacement it is dependent on equation 2 and equation 1, which is biharmonic function, and I mentioned this in a very detailed manner in the previous videos. So this is equation 3, right? And the code of this equation 3 is included in this lecture as well. So if you have purchased this course, you will have a detailed, well structured code with yourself, which should be somewhat like this, but this is the architecture of the code. So this is only for the understanding purpose, right? So let's go to equation 3. I don't need equation 2 anymore. I visualized it already. Let's go to the vertical displacement component, which is visible here, and let's try to edit it with simulate it or run it with equation 1 and equation 2. So let's go to run module here. But before that, I should change the inputs here. Look at here, I have the input of 3500, whatever the units are, and Poisson ratio. Similarly, this should be 0.5, this should be 1, and I will show you the pattern here as well. So let's see what does this code do. These are very interesting lectures. I wish I study more and more about the nature of the pattern data. So for vertical displacement, this is radial displacement, which we don't need, but this is the vertical displacement that we are observing here. So the vertical displacement should be maximum on the top, right? And it should be in radial direction. It should be minimum at the ends, which is the nature of the problem. But I have applied a Gaussian smoothing parameter on it, which was to control the deformation here. So this is for vertical displacement component, and let's go back to our ABAQUS problem. The vertical deflection, which I am expecting here, it should be maximum here, right? But since it's a positive sign, so in order to make it with the in the sign is associated with the vertical displacement here, I should change the sign of this parameter here. So let's do this. But before that, let's delete from the code this pattern, because I don't need the radial displacement here. I only need the vertical displacement here. Similarly, I will do this here as well. In this, already I am getting the vertical displacement, the radial displacement, sorry. So let's just delete that and save this document here. Look at the code again, and here in this code, for this vertical displacement, I should convert this sign to negative so that it resembles the notation of the ABAQUS file which we are using right now. So let's run this code and let's see what's going on here. So you can see now, here is the load which is applied here, and it is giving us a maximum vertical displacement. Then there is a rutting phenomena on the top of this location away from this pattern. And in Gaussian smoothing, the deformation is controlled here, but it is approximate estimation of the vertical displacement that we are getting here. So let's look at the ABAQUS file. Let's go to the path again, go to the results and switch to the U1 component, and it will switch to the U2 component, It will take some time, but we can see here the maximum settlement routing profile is here, and we have minimum option here. So the model is although a stiff model because we are not using infinite element, but this is a correct estimation. I mean, we are getting a maximum value here, right, and minimum value here. But since, as I mentioned, we are not consistent in unit, but along the radial direction, if you look at here at the radial direction, we are having the same pattern, just like the way it is shown here. So let's go to the pattern here. Let's go to plotting here, and yes, you can see here. So it is starting at this region, and in this manner we are getting this routing profile, which is somewhat like this. So this is the estimation from LET theory, and this is the visualization of ABAQUS profile, right? So you can see how easy and conceptual it is when we are dealing these with respect to LET theories, and this is the origin of the multi-layer system, which has arised a lot of questions on it, and in order to solve it, we need to explore these codes and these equations, right? And in order to understand this, we need a lot of efforts in our simulation files before going forward. So I will stop my lecture at this point, and then I will continue further in the next videos on how to discuss the vertical stresses and radial stresses in horizontal plane and tangential stresses in horizontal plane. Similarly, we will discuss the shear stresses as well. So these are the main equations which I am going to cover in this lecture series. Thank you so much for watching. Have a good day.